Today we're going to continue our lesson on electrochemistry. This time we're going to talk about corrosion. Corrosion is essentially unwanted oxidation. It's the oxidative deterioration of a metal. And probably the one we're most familiar with is rust. Rusting of iron requires both oxygen and water to take place. Rust is iron 3 oxide hydrate. The thing about rust is that it's very soft, and so when rust forms on the surface of iron, it flakes off, exposing more metal underneath. Okay, so how do we prevent corrosion? Okay, for some metals, they form a tough oxide skin, which protects the metal underneath. And examples of this include aluminum, chromium, magnesium, titanium, zinc, and there are some others. Aluminum in particular, aluminum is reactive enough where you don't see it in pure form in nature. It's always combined with something. The same way with magnesium. But when exposed to the air, they quickly form this tough layer on the outside which protects the metal underneath. One method of protecting from corrosion is something called galvanization. Galvanization specifically refers to coating iron with zinc. Now, galvanized steel has this light gray color because of the zinc coating. Okay, because zinc is more reactive than iron, it forms an oxide coating, and galvanized steel that has been exposed to moisture and air for a long period of time will often appear white because of the zinc oxide. Even if the zinc coating is scratched and the iron is exposed underneath, once the iron starts to rust, then zinc donates electrons and reduces the iron back to iron metal, and therefore prevents rusting. Okay, so here are the two half reactions. When some of the iron is oxidized, the process is reversed, since zinc will reduce iron to iron. Okay, another way of preventing corrosion is cathodic protection. And instead of coating the entire surface of the first metal with the second metal is placed in electrical contact with the first metal. Okay, some of the places where you see cathodic protection include pipelines and offshore oil drilling platforms. It's impractical to plate the entire object. And so in the case of pipelines, what they usually do is they'll tie a wire around the pipeline, and then that wire will go to a stake which is buried. The stake is made of magnesium or aluminum or zinc. And as the iron starts to rust, the more active metal will donate electrons to the iron and reduce it back. The magnesium in this example, stake, will deteriorate over time, and so it has to be replaced periodically. And so it's called a sacrificial anode. Metals are electroplated by a process called electrolysis, where we supply a external electric current to bring about a chemical change. So here again is the table of standard reduction potentials, and electrons will flow spontaneously from higher up on the chart to lower down. But in order to reverse the process, we can supply an electric current. One of the ways of producing, well, this is the main way of producing sodium, and that is through electrolysis. In fact, a number of elements, particularly the group 1 and group 2 elements, and also the halogens, are produced by electrolysis. In the case of sodium chloride, what they do is they'll take sodium chloride and melt it. Okay, it requires about 800 degrees Celsius in order to melt the sodium chloride. And an electric current is supplied. Chloride is oxidized to chlorine gas, and sodium ions are reduced to sodium metal. Okay, so that shows the process schematically. In order to obtain sodium metal, we need to use molten sodium chloride. Now, in the case of aqueous sodium chloride, we can't obtain sodium this way because the sodium would immediately react with the water. But this is done on a large scale in a number of locations. In fact, there's a major plant near Wichita. It used to be called Vulcan, and then it was OxyChem, and I think it's BASF, or maybe now it's still called OxyChem. But they produce chlorine from sodium chloride. There's an abundant source of sodium chloride with the salt mines nearby in Hutchinson, but it's very expensive to produce chlorine by electrolysis. In fact, their electric bills are $2 to $3 million a month. But they produce a lot of chlorine, and the major use of chlorine is disinfecting water supplies. There were some locations, even in the United States, that discontinued chlorination, and they suffered several instances of waterborne diseases as a result. In 1990, the country of Peru discontinued chlorination, and as a result, they had several thousand cases of cholera. Chlorine is also used in plastics, such as polyvinyl chloride, and a number of other applications. The byproduct of this is sodium hydroxide, which they also sell. Water can be electrolyzed into its elements, hydrogen and oxygen. Okay, this is the down cell that's used for producing sodium metal. This uses the molten sodium chloride and uses a graphite anode. And there's an iron screen that keeps the sodium and chlorine away from each other. Otherwise, they would just reform sodium chloride. The molten sodium is less dense than either the sodium chloride or the calcium chloride, and so it sinks to the bottom. And then there is a vent up at the top to remove the chlorine gas that's produced. Okay, this is a membrane cell. This is much like what they use at the plant in Wichita for producing chlorine and sodium hydroxide. Okay, another element that is produced by electrolysis is aluminum. Aluminum in the early 1800s was very difficult to isolate. What they did was they took molten aluminum oxide, which required a very, very high temperature to melt. And aluminum was so difficult to obtain that some of the royalty, such as Napoleon, actually had aluminum utensils. In the 1880s, there were two individuals, Charles Hall, who was an American, and Henri Hérault, who lived in France, independently discovered this process. And if you take a mixture of sodium hexafluoroaluminate and aluminum oxide, that has a lower melting point. So that requires a lower melting point than aluminum oxide alone. So that requires less energy, and so it's easier to produce aluminum. The cathode consists of a graphite-lined tank, and then the anode is also graphite. So an electric current is passed through here, and molten aluminum is deposited down at the bottom. And the molten aluminum, being more dense, is then drawn out. Aluminum requires a tremendous amount of electricity to produce. The aluminum ion has a +3 charge, so it requires 3 electrons to produce 1 atom of aluminum. Although aluminum is the most abundant metal in the Earth's crust, there's an emphasis on recycling aluminum because this process is so energy intensive. In fact, it only takes about 5% of the energy to obtain aluminum by recycling compared to refining new aluminum. Okay, here we have electro-refining of copper metal. So we have alternating slabs of impure and pure copper. Okay, there's actually a potential difference between those two, and they serve as electrodes in electrolytic cells for the refining of copper. Okay, in the process, more easily oxidized impurities, okay, like zinc and iron, will remain in solution as cations. Less reactive impurities, such as noble metals like silver, gold, platinum, and others, are not oxidized, and they collect down in the mud down here at the bottom. So the reason for doing this is not so much to make ultra-pure copper, but it's to obtain these noble metals. This is really where they make their money. Okay, finally, we're going to look at the quantitative aspects of electrolysis. And we introduced this idea of Faraday's constant early on. This is the charge on 1 mole of electrons. An amp is a coulomb per second, is defined as a coulomb per second. A coulomb would be an amp times a second. Okay, so we can calculate charge, we can calculate current, we can calculate time depending on what information we have. Okay, once we have the charge, okay, we can figure out how many moles of electrons that is from Faraday's constant. Okay, so if we are given, for example, current and time, we can find the product of current and time, which is charge. We could use the Faraday as a conversion factor to find moles of electrons. And then we have to be mindful of the coefficients in the balanced equation. For example, I talked about how aluminum has a +3 charge. So for every 3 moles of electrons that are used, we produce 1 atom of aluminum, or 1 mole of aluminum. Okay, and then from that we can obtain moles of product, and then we can use molar mass or standard molar volume or the gas law to determine grams or liters of product.